How's it going? This is Tim here. Hope you're doing well. This is a little tutorial on some of the maths questions um, that I was teaching on mechanical power, torque and force. And a lot of you asked for just a quick video to go over these questions, so here it is. All right, well look, I'll get moving on it. Question number one. We have a poor lad is pulling a box across the floor. The wooden box weighs 400 pounds of weight. The floor is clean and dry. He's a strong lad, but he can only muster 75 pounds of pulling force. So this chap he's pulling 75 pounds of force on that rope. The box, of course, is not going to move because there's static friction between the bottom of the box and the concrete floor. Now, if that's going in this direction, the force of static friction is going in this direction. This is my first time writing on a PDF, so forgive me. The equation for static friction, we're gonna call it F, is equal to mu times n. That's that Greek letter that stands for the coefficient of static friction. Now, I need to know the coefficient of static friction. This is a wood box and this is a concrete floor. Now, of course, I didn't give it to you here. Here's my table of static versus sliding friction, but I've only given you steel on steel or glass on glass or metal on metal. So let's have a look. Let's type in coefficient static friction. Oh Lord, it's 9 o'clock in the morning. Between concrete and wood. The coefficient of static friction between wood and concrete is 0.2. And if you have two different materials, you can always type that in and they're going to come up. You could have the coefficient of between gold and silver, maybe, I don't know. All right, so the mu in this case is 0.2, and then we're going to multiply that by n, which is the force coming, the weight of that box coming down in that direction, which is 400 pounds. All right. Now, 0.2 multiplied by 400 pounds is equal to 80 pounds. So this box is fighting back, is putting 80 pounds of frictional force against 75 pounds. The box is not going to move. He's just not strong enough. He needs to get help, or he needs to start lifting some weights and then come back to it. All right, that's question number one. Will the box move? No. All right, let's go on. We move on to question number two. Let me have a little sup of coffee here. We have a large box, W. It is a weight of 400 pounds. It's made from steel, and the floor is steel. What should the minimum weight on the end of the pulley be to get it moving? Okay, well, there's no oil on that. We'll get this part of the question on first, and then we'll do the oil. Hold on, make sure this better be recording here. That's all right. Now, all right, let's have a look again. Our equation is F, which stands for static friction, is equal to mu, looks like a U with a little tail, multiplied by N. Now the mu in this case is steel on steel. So I'll go up here, steel on steel, 0.74. So that's a fair amount of static friction, yeah. A 0.0, That's a pretty high coefficient. 0.74 multiplied by 400 is equal to, calculator, 400 multiplied by 0.74 is roughly, we'll say, 296 pounds. So this way, the weight of this block is going to cause a static friction in that direction against the rope of 296 pounds. We need roughly about 300 pounds pulling in this direction to even get that block to move. Once that block gets moving, the sliding friction of steel on steel is less, so it's going to get moving. If we apply 300 pounds, so this weight needs to be 300 pounds. There's a little pulley system coming down, and that'll get the block moving. Now, what happens if there's oil on the floor? If there's oil, a little layer of oil on this floor here, it's going to separate the steel on steel, and it's no longer, this mu here is going to be no longer static or sliding. This would be a fluid friction. So let's have a look. If we go metal on metal lubricated, it's 0.15. So what we'll do is we can put calculator, 400 multiplied by 0.15, I could get away with 60 pounds of force here. I could get away with 60 pounds, and that will definitely get that block moving a lot easier. So lubrication is our friend. So that's question number 2. All right, question number 3. How much force does the blue stick man have to put on the end of the lever if the mass at the end of the lever weighs 120 pounds? So this is 120 pounds, like so. How much force does the little blue man have to put on the end of the lever? Okay, now what I do, and I don't know if this is right, but what I do when I'm doing these problems, remember this is the fulcrum or the pivot point. What I do is I'll go, the torque on the left is equal to the torque on the right. In order for this thing to be balanced, the torque on the left needs to be equal to the torque on the right. And the torque on the left, and this is going to be the minimum amount of force to even get this lifted. We would need to add more force. But look, obviously we have a long arm here, a long lever arm, so it's going to be less than 120. I can tell by looking at this that it's just this ratio between these two multiplied by 120. But let's do it this way. So the torque on the left is equal to the force on the left multiplied by the distance on the left is equal to the force on the right with a little r multiplied by the distance on the right. Okay, now what's the force on the left? It's 120. Oh, that looks terrible. It's okay. 120 multiplied by 4. Look at that. One little dash stands for feet. The force on the right we don't know. We're trying to figure that out. Hopefully he's strong enough. Multiplied by the distance on the right, which is 12. Now, 4 times 120 is 480 is equal to F R multiplied by 12. Now even I know if I want to get rid of 12, I got to divide by 12 on both sides. Oh Lord. Let's try that again. Undo. So Oh my god. 48 divided by 12 is 4. Oh my god, 40. So FR is equal to 40 pounds. 40 pounds. Alright. So this chap has to apply a downward force of at least 40 pounds to get that 120 up. He needs to muster about 50 pounds of force, and he'll lift that 120 pounds up, no problem. Another thing, what he could do is instead of having that lever 4 feet away, he needs to bring this lever even have a longer lever on the right hand side, and that'll help. All right, question number 4. If the scales are balanced, what is the weight of the apples if the bucket weighs a quarter of a pound? So believe it or not, yeah, this is how, before you had an electronic scales, a vegetable or a fruit shop this is how they would weigh their apples or their fruit or their vegetables. Now we have 2 pounds on this side, we know that. We need to calculate what is the total weight of the apples and the little bucket. So again, I write TL is equal to TR. The torque on the left is equal to the torque on the right. So I have FL, torque is equal to force times distance, you know that, is equal to 2 inches, is equal to 2 pounds multiplied by, oh that looks terrible, let's try that again, 12 inches. So FL is equal to 24 divided by 2. I'm thinking here, 24 divided by 2 is equal to 12 pounds. Alright, the total weight of this apples and the bucket is 12 pounds. If the bucket weighs a quarter of a pound, the weight of the apples, WA, I'm not writing apples out, is equal to 12 minus 1/4, which equals to 11.75 pounds. Alright, question number 5. How much force is required on the right side to balance the 2 weights on the left? Oh, sure, this is easy. Okay, so how much force on the right side? So I'm going to go the torque. What's the total torque on the left side? It's equal to F1 times D1 plus, there's 2 forces, I'm going to have 2 separate torques, plus F2 multiplied by D2. Now F1 is going to be 20 multiplied by 10 plus 30 multiplied by, oh stop now, multiplied by 5. So that is 350 foot-pounds of torque. All my brain is trying to concentrate writing with this mouse. Alright, so the total torque on the left is 350 foot-pounds. The total torque on the right, if these things are balanced, it's going to be 350 is equal to 10 foot multiplied by question mark. So the question mark is going to be equal to 35 foot-pounds. That's funny. Let me think about this for 35 foot-pounds. Yeah, it's the 20. Yeah, this 20 is not doing much good. Being it's a small force. 35 foot-pounds will balance that, being that far away, 10 foot out. Yeah, that makes sense. 35 foot-pounds is the force required on the right side to balance the two weights on the left. All right. Um, the specs for the shop crane. Now, this is poorly worded. The length of the boom arm from there to there is 5 feet. Okay? What the question is, what is the torque on the crane if this is lifting 1 US ton? Okay, so the little trick there is, what is a ton in pounds? And I'm thinking it's 2,000 pounds, but we'll find out. 1 US ton in pounds. 1 US ton is equal to 2,000 pounds. All right, so let's go back here. So the torque, T, is equal to the force times the distance, and the force is 2,000 pounds of force times 5 feet, which is equal to 10,000 foot-pounds. Now, I would bet money if you buy a crane like this, I don't know, a boom crane, if that's what it's called, or a winch crane, it will tell you the maximum load at the furthest point on the span. I wish I kept the number of this, but anyway, that's the total torque. All right. Question number 7. What is the total torque in foot-pounds on the wrench below? Hopefully you remember, this point here is called the pivot point, or the fulcrum, or the axis of rotation. And whenever we measure torque, it's always from that distance out to where the force is applied. So the total torque, T, is equal to, I'm going to call this FB multiplied by DB. That's the total torque due to that hand, plus FA multiplied by DA. Hopefully you understand why I'm multiplying between these two and just adding between. So this is the total torque due to this hand. This is the total torque due to this hand. We have two hands. We don't multiply the two torques, we add them. So this is 10 pounds, forgive my writing, multiplied by 1 foot, 12 inches. 12 inches is equal to 1 foot, plus 10 pounds multiplied by a half a foot. And what's the total torque? It's going to be 10 plus, it's going to be 15 foot-pounds. I hope I'm right there. Yeah, 15 foot-pounds. If this was a torque wrench and I had the torque limited to 10 foot-pounds, even though I'm applying 15 foot-pounds, only 10 foot-pounds will be transferred on the torque wrench, because the other 5, it will slip once it reaches 10 foot-pounds, on average of 10 foot-pounds. All right. If you started with me and you're on working through number 8, give yourself your head and out break, walk away from these out maths for a few minutes and come back. All right, let's have a look at question number 8. Yeah, she's recording, that's good. All right, we have two I know this looks crazy, but we have two drums that are connected. Well, it looks like this is a drum and this is the shaft, and both of these are connected. The drum has a force of 3.2 pounds going in that direction. Now this is going clockwise, this is going anti-clockwise, and this is a force of 4 pounds. So basically these two forces are working against each other. Is that right? Yeah, they're working against each other. And the distance from, now this point here is the magic point, it's the fulcrum. From there out to there is 2 feet. And from here out to here, I can see is 6 feet. Now I'm trying to trick you here by calling these the diameters of the large circle and the diameter of the small circle. Whenever we're measuring the torque, it's always from the pivot point out to the point of the force. So whenever, if I say the diameter of the large circle is 12 feet, you divide it by 2. Now, does the system rotate clockwise or counterclockwise? So what we'll do is we're going to call this T1, force 1. What is the torque due to the force 1? So we're going to call this T1 is equal to F1, force 1, multiplied by D1. So it's 4 pounds multiplied by D1, which is going to be 2 feet. So the total torque, T1, is equal to 8 foot-pounds. Alright? Now, let's look at torque number 2. Torque 2 is equal to force 2 multiplied by D2. That's equal to 3.2 pounds multiplied by 6 feet. Oh yeah, that's at least 18 foot-pounds. Let's get the old calculator going. 3.2, no, let's try that again. 3.2 multiplied by 6, 19.2. foot-pounds. What's going to happen? The system is going to rotate clockwise, no trouble. And why? Because of this big moment distance. Alright, 19.2 foot-pounds. What's the total torque on the system? The total torque on the system is 19.2 minus 8. So there is the torque is 11.2 foot-pounds in this direction. Okay. Now, let's have a look. Question number 9. The average jam jar needs about 40 inch-pounds of torque to open. That's what it says. I found that on the internet. The diameter of the jar is 3 inches. What is the minimum force on the scale to open the jar? How much force? If I pull this scale, what is the minimum force that'll open this up? So, torque is equal to force times distance. Now this is in inch-pounds. So I'm going to write this down, 40 inch-pounds. Is equal to force. We don't know that. We want to know the minimum force times the distance. Now, the diameter of the jar is 3 inches. If we look at this jar from the top down, oh god, that's a terrible circle. It looks something like this. The distance from the force to the pivot point is going to be 1.5 1.5 inches. Look at that, terrible. 1.5 inches. All right. So we're going to put down 1.5 here inches. Now 40 divided by 1.5 is 26.66. So the force is roughly 27 pounds is what we need to be able to apply, and we'll get that jam jar open. 27 pounds of force. Okay. Question number 10. How many of these do we have to do? Oh Lord, 17. Alright, question number 10. The motor shown can provide a max torque of 4 foot-pounds of torque. So this motor here, there's your motor, there's your gearbox, and there's your winch. This can provide 4 foot-pounds of torque. If the diameter of the winch drum shaft, this thing right here, is 1.5 inches, what is the maximum force the winch can lift? What is the maximum weight the winch can lift? So where am I going to write this down? We're going to write down torque is equal to force times distance. The torque in this example is 4 foot-pounds. We want to find out how much force this bad boy can lift. The winch drum shaft is 1.5 inches. Oh, be careful. That's this distance here, the diameter. See how when you start going on autopilot, see what happens. The distance from there to there, we want is the radius. We divide this by 2. That's 0.75 inches. 0.75 inches. We have to get this in feet. So calculator, it's only 0.75 divided by 12. Let me write that down on a piece of paper. 0.0625 feet. So it's 0. I had to divide that by 12. I had to divide it by 2 to get it as a radius, then divide it by 12 to get it in feet. 0.0625 inches, not in feet. So let's go back. This is going to be a very large weight. Now, so it's 4 divided by 0.0625. So this can lift a force of 64 pounds. No problem. As the spool goes round and round and round, and that radius gets bigger, and it gets round and round and round, you actually find out whenever you have a winch, as the motor has to work harder because of this drum shaft starts to increase as it starts winding around the winch. But the maximum force the winch can lift is 64 pounds. Yeah, that's the maximum force. Yep. So you probably wouldn't want to lift anything higher than 50 pounds with this winch setup. All right, let's have a look at question number 11. The self-closing mechanism on the door provides a torque of 15 foot-pounds. 15 foot-pounds to close the door. It has, okay, there's a spring on it. A typical door width is 3 feet. All right, 36 inches. How much force does a person need to open up the door? This is a nice torque question. So, let's have a look. So torque is equal to force times distance. The torque is 15 foot-pounds. The force we don't know. The distance is, we're not going to put down 36 inches because this is in feet. Let's put down 3 feet. If this concept of when to use inches and when to use feet confuses you, what I tell my students is just keep everything in foot pounds. So if I give you a distance, number one, it's always going to be the radius. It's never going to be the diameter of anything. And then always, whatever the distance is, make sure it's in feet. So if it's 36 inches, just divide it by 12. So the force, I divide 15 divided by 3, and I'm going to get 5 pounds of force. So how much force does a person need to open up the door? At least 5 pounds. If it's anything under 5 pounds, God love them, the spring is too strong. So that's it. 5 pounds of force. Now, we have, this is a crank and this is a winch. What is the maximum weight the winch below can lift, assuming the user can apply an average force of 10 pounds on the crank? So somebody has their arm, they're pushing on this crank, the max they can put in there is about 10 pounds. How much weight can this lift? Oh, that's a nice little question. Right, I'm thinking about this. This is actually tricky, a little bit tricky. So we have a crank, and if we apply a torque, if we apply a force here, that's going to cause a torque inside of that shaft. So let's find out how much torque this 10 pounds is applying. So we'll go torque is equal to force times distance. That's going to be 10 pounds multiplied by, what is the distance of, what is the length of the crank? The crank length is 10 inches. So let's put that in feet. So it's going to be 10 divided by 12. That's 0.83 feet. 0.83 feet. And that's going to give us a total torque on this little shaft of 8.3 foot-pounds. Is that right? 8.3 foot-pounds. If this rope was on that exact shaft, that would be if that was on that exact shaft, I'd have to think about that. How much force would that thing be able to lift? It depends on the diameter of the shaft, yeah. So hold on a second. That's the total torque that's on that shaft. I need to think about this. Now, just bear with me here. So this torque is provided, this crank is providing a torque on that whole winch of 8.3 foot-pounds. If we want to calculate what W is, I can write torque, and I have to think about this stuff, is equal to force times distance. We have 8.3 foot-pounds is equal to F. We don't know what that F is, multiplied by the distance from the fulcrum out to that. Now we're saying the winch drum diameter is 4 inches. The radius is going to be 2 inches, and we have to divide that by 2. What do we get? So it's 2 divided by 12 is 0.166. So this is 0.166. Now why did I divide that by 12? Because this is in that original distance, it's in feet. So let's go 8.3 divided by 0.166 is equal to 50. So F is equal to 50 pounds. That is the maximum weight that winch below can lift. 50 pounds. Now you're probably thinking to yourself, how the hell can that lift 50 pounds when I'm only applying a 10-pound force here? And what this is, it's an example of force multiplication. We've a big long arm here, essentially there, and then we have a smaller arm. So we're going to have to do a lot more winding, a lot more winding. The distance here, the turning distance will be less, but we gain force. This is a force multiplier. So hopefully that hasn't confused the hell out of you. That's question number 12. Question number 13. Excuse me. All right. It's a good little question now. Now, an electric motor is used to drive a water pump. There's your electric motor there. There's your coupling. There's your water pump. The motor provides a torque of 100 inch-pounds. Now right away, let's get rid of that inch-pounds and let's convert it into foot-pounds. So we'll go 100 divided by 12 is 8.33. So the torque is 8.33 foot-pounds. Boop. How much work does the motor accomplish in 40 revolutions? Remember, work for a rotational system is torque times angle moved. That's our equation. When using this equation, remember the angle moved must be in radians. So I can't just multiply 40 times 360, that's the degrees. We're going to be using radians. Why? Because it makes the maths easier. Now, so work. Now I like to write down a little R here to indicate that this is rotational work is equal to torque times angle moved. I apologize in advance for the writing. Angle moved. All right. What's the torque? It's 8.33 foot-pounds times the angle moved, which is 40 revolutions, multiplied by, if it's 1 revolution, is equal to 360 degrees, but 2 pi radians. So I just put in 2 pi here. And what will I do? I'll multiply this out. 6.28, which is the 2 times the pi, multiplied by 40, multiplied by 8.33, gives me 2,092 foot-pounds of work. So it's doing a fair amount of work, okay? Rotational work, okay. Easy enough. All right. Look at this lovely diagram I stole from the internet. We have an elevator or a lift. We have a motor. We have a gearbox that slows down the motor, and gives us the torque. And what have we got here? This is a winch. Okay. So when the motor's on, it turns the winch. This goes up and down. Everybody's happy. Shown below is a typical setup for an elevator. Your job is to determine a suitable AC motor for the system. The typical weight of the elevator, car and passengers is 4,000 pounds. The building owner has specified the elevator should be able to travel from the lowest floor to the highest floor a total distance of 300 feet in at least 10 seconds. Oh my god. Now, hopefully you realize whenever you see a distance and you see time and you see force, that is a power question, a linear power question. And the equation we use is power. I'm not going to write out power. This is an example of a linear power question. And power is equal to work divided by time. Time is very important. Now, that is equal to force multiplied by distance divided by time. Okay? The force in this example is how much weight it is. It's 4,000 pounds. The distance is, it needs to be able to travel from the lowest floor to the highest floor, 300 feet. Oh, that looks terrible. 300 feet. Let's even put that, there you go, in 10 seconds. So 4,000 multiplied by 300 divided by 10 is equal to 120. My god, big numbers. 120,000. I think the owner's dreaming. It's not going to travel that fast. 120,000. Now the units, we take the units based on the actual equation. So this is foot pounds a second. Now hopefully you remember from horsepower, this is a constant. 1 horsepower, HP, is equal to 550 foot-pounds a second. So this is going to be a pretty big motor. So 550 foot-pounds a second. This is a constant. James Watt figured this out. So let's go 120,000 divided by 550 is roughly 218 horsepower. Now let's go to McMaster car and see if we can find a motor that big. We'll find a motor, AC motor. Oh god, 5 horsepower or greater. Max horsepower is 10. So what do we do? I want to find a 200 horsepower electric motor. I wonder, does it have to be DC? Wow, look at that. There's a 200 horsepower motor. Beast of a thing. 3-phase. I wonder how big that is. Beast of a thing. Yeah, you're talking big numbers. Yeah, look, if that's the size of a pallet, it's a beast of a motor. Yeah, decent size. Yeah, so let's have a look at how many more of these we have. We've got 3 more. We're nearly there. We have a gearbox. No, we have a motor. We have a gearbox. We have a winch. In the system below, at a fast setting, the drum rotates at 24 RPM. 24 RPM is the speed. The slow speed is 12 RPM. The drum diameter is 6 inches. What is the power required to lift 1,000 pound weight at both speeds. Okay, now I can tell you right now, at a faster speed, we're gonna need more power, and I bet you money that it's half the horsepower for 12 RPM. Now, the equation that I like to use horsepower is equal to speed multiplied by torque divided by, remember the numbers, 52, 5,252. Okay, the speed is going to be in RPM, the torque is going to be in foot-pounds. Now we know the speed right off the bat is 24, but we don't know the torque. The torque is equal to force times distance. The force is going to be 1,000 pounds. The distance is going to be the radius of the drum, and that's going to be 3 inches, but we divide that by 12. 3 divided by 12 is a quarter, so it's going to be 0.25 feet. So that's going to be equal to, the torque is going to be equal to 250 foot-pounds. Is that right? 250 foot-pounds. Now, let's throw the torque we just calculated up into this equation, and we're going to go HP is equal to 24, which RPM, multiplied by torque, which is 250, and we're going to divide that by 200. Now, what are we doing? 52. Where did I get that number from? It's a constant. So just go with it. Be happy that it's a simple constant. 52, 52. Calculator. 24 multiplied by 250 divided by 52, 52. I need a motor in order to run this at 24 RPM, and in order to lift up 1,000 pound, that 1,000 pound weight, I need a motor that's at least 1.14 horsepower, but really it should be bigger. Now, I can do this equation again. That's at the fast speed. I know I can just divide that number by 2 and it will work out, but let's just do it. It's equal to, now the low speed is 12 RPM multiplied by 250 divided by 52, 52, and it should be roughly about a half. Now this is going to be the slow example, at a slow speed. 12 times 250 divided by 52, 52 is equal to 0.57 horsepower. Hopefully that doesn't shock you. Like whenever we're running something slowly or at a lower speed, you have a less of a power requirement. If we wanted to run this at 48 RPM, again it would be double. We would need double the horsepower. So, what is the power required to lift 1,000 pound weight at both speeds? The first one was like 1.0 something, and then the second one was 0.57 horsepower. Okay, question number 16. My Toyota Tacoma engine specs say it is 159 horsepower. If the engine rotates at 4,000 RPM, you can see this in the dashboard engine revs. How much torque can the engine produce? Now, let's undo what I just did there. I'm How much torque I'm just talking about the engine now. I'm not talking about putting it through a gearbox, or hopefully that actually makes sense to you. Now, so what is the equation? It's horsepower is equal to torque. God almighty, you'd swear I'd never written before in my life. Times speed, or speed times torque, divided by 52. I just don't have a whole lot of space. Let's zoom in and make it easier for myself. Okay, so we say 159 is equal to T for torque multiplied by 4000 RPM divided by 52. This is just a simple horsepower torque equation. And so let's do this. I'm going to multiply 159 multiplied by 52, and I get 8,000, never mind. Divide that number by 4,000 and I'm going to get a torque of roughly 210 foot-pounds of torque. Let's have a look. Let's look at the torque output of Tacoma Toyota. This is embarrassing. Toyota Tacoma engine, 4-cylinder. It's thinking. It's saying 180.26 nanonewton meters. Let's see what that is in foot-pounds. Is it saying 180 to 265 newton meters? So if I go 180 newton meters in foot-pounds, what do I get? Aha, I get 132, but let's put in the 265. 265 newton meters is equal to 195.45 foot-pounds. And what did I get? Near roughly 200 foot-pounds. There you go. I wasn't lying. It depends on the speed. It depends on the speed of the motor. And I bet you money at 4,000 RPM, that's where you get your maximum torque coming out from the output of the engine. All right. God almighty. The last one. Oh. What the hell was I thinking writing this many questions? A conveyor system requires a torque of at least 20 foot-pounds to transfer heavy barrels. We know it needs to provide 20 foot-pounds. The motor speed also needs to be 100 RPM in order to keep Baltimore in beer. Okay. What is the maximum HP size of the motor? So this is easy. Look. I'll just write down the equation. Horsepower is equal to torque times speed divided by 52. I'm pretty sure this can be a pretty low horsepower based on these specs. I'm just that good. Now, let's have a look. I'm joking. Torque is 20 foot-pounds. We don't need to write that down. Multiplied by 100 RPM divided by 52 is the total horsepower. So 20 multiplied by 1,000 is 20,000 divided by 52 is equal to, is that right? 3.8. And we could even get that motor on McMaster car. 3.8 horsepower. Look, in the real world, we would not get a 3.8 horse. You can't get a 3.8 horsepower motor anyway. You would increase this. You would double that number, just so you have a safety factor. Alright, look, hopefully this wasn't too painful. But there you go. There's my that's your tutorial in force, torque, work and power. Take care and I'll see you in class.